let me move with the first section of the talk about these evidences. So on this slide, you have some SN curves obtained on an aluminum, copper, magnesium alloy. So maybe I can start from this slide. So presenting SN curves obtained on aluminum, copper, magnesium alloys loaded in banding with two different heat treatments corresponding with different hardening precipitates, namely theta double prime or Guinea-Preston zones. And what you can see is that for a given microstructure, for instance here, the microstructure hardened by theta double prime precipitates, you have a significant decay in the fatigue strength when the material is loaded in an active environment such as air. And actually, some additional analysis indicated that it is the presence of moisture in this type of environment which is responsible for this loss in fatigue strength. However, at this stage, it is difficult to say whether this decay in fatigue strength is related on an effect of moisture on crack initiation or on crack propagation or on a combination of both. So in order to address this issue, here we can consider some results obtained by the group of Professor Mugrabi in Germany, where we have some observations of the surface of specimens of a copper single crystal, which has been cyclically deformed during low cycle fatigue. So on the left-hand side, you have low magnification views of the formation of extrusions in bright and presumably some intrusions in some dark areas. And on the right-hand side, a higher magnification view. So where you can clearly see here some examples of extrusions and also some intrusions and perhaps the beginning of crack initiation. However, when comparing these observations between air and vacuum for a given value of the cumulative plastic strain, what was concluded is that there is no significant difference in the surface relief which is formed for a fixed value of this cumulative fatigue, plastic strain. And this was confirmed by the results obtained by Hunsche and Neumann, again on a single crystal. On this graph, you have the measurements of the average extrusion rate as a function of the cumulated plastic strain, and for measurements obtained under different environmental conditions, namely ambient air, argon, ultra-high vacuum, and oxygen. And what is noticed is that you have almost a single relationship between the height of the protrusions as a function of the cumulated plastic strain, regardless of the testing environment. And so the conclusion from all these observations was to say that environments such as ambient air does not influence the kinetics of the formation of the surface relief, but will mainly act on the initiation process and most probably on the growth of small and then long cracks. So again, here an example dealing with low cycle fatigue in the case of austenitic stainless steel 316L, deformed under cyclic plastic strain control with this value of the cyclic plastic strain amplitude. And on this graph, you have the variation of the number of cycles to failure as a function of temperature, with some data collected in air and in vacuum. And what you can see is that in air, you have a gentle variation of the fatigue life as the temperature increases. The number of cycles to failure decreases. However, when looking at the data obtained in vacuum, you can see that we have a maximum in the fatigue life, which is much higher, around 300 degrees C, and then decreases again. And at 600 degrees C, the difference between air and vacuum is not so large. And this special behavior in vacuum was explained by looking at the internal dislocation structure, where it was shown that at low temperature, you have a classical cell formation, dislocation cell formation. And when temperature increases, this structure evolves towards the formation of this special microstructure consisting in lines of dislocation, which is called the corduroy structure. And again, when moving to higher temperature, you modify, you disable this corduroy microstructure, and you find something corresponding more or less to the cell structure. But the point is that if you perform the same type of observations in air, you will not observe the corduroy structure at 300 degrees C, because failure will occur much earlier during the fatigue life due to the assistance of the environmental effects. Okay, and typically the deformation internal structure that you would observe in air at 300 degrees C would be only a snapshot of the evolution of the dislocation structures towards this corduroy structure. And this is very important to keep in mind the fact that what you observed in air is just a moment during the fatigue life. So again, here an example about low cycle fatigue of austenitic stainless steel, in that case, a 304L steel. And here we compare the fatigue response in 3 different environments, namely vacuum, considered as an inert environment, ambient air, and a PW, pressurized water reactor environment, which is the actual operating condition in nuclear power plants, especially in France. And so as expected, first, what you can see is that globally, the cyclic stress-stress response is not affected by environment, but we have an effect of environment on the fatigue life. And as expected, in the PWR environment, the fatigue life is much less than in air. However, if we compare air with vacuum, you can see that the difference in terms of number of cycles is much larger between air and vacuum than between air and PWR environment. So that means that environmental effects are already present in air and has a large effect on the fatigue life. And this raises the question of the fact of selecting air as a reference of environment for the design codes of this type of structures, typically piping systems in nuclear power plants. So here, another illustration, in that case for fatigue crack propagation, in a case of 2024 aluminum alloy, where we compare the fatigue crack-off rates for different environmental conditions, namely ultra-high vacuum conditions here, which is in that case characterized by a special crack propagation mechanism that I will detail later on. And then some water environment, namely distilled water and a saline solution with different loading frequencies, and finally air. And what you can see is that the fatigue crack-off rates in air, in most cases, are similar to the fatigue crack-off rates obtained in liquids, especially at low frequency. And in that case, we need to move to quite high frequencies, typically 5 to 10 hertz, in order to induce an environmental effect which is larger than the environmental effect induced by ambient air. So that means that in many cases, ambient air is at least as aggressive as other environments which are assumed to be corrosive. Another evidence of the influence of ambient air as an active environment is when looking at the fracture surfaces, here in the case of an aluminum copper magnesium alloy. And in these experiments, we changed the environment during propagation. So for instance, on the left-hand side, the propagation first takes place in air. And at this stage, we switch to vacuum. And as you might know, what you can read in textbooks is that generally fatigue crack propagation, especially in these alloys, is associated with the formation of striations on the fracture surfaces. And indeed, in air, you observe in that case quite nice striations. However, when you switch to inert environment with the same load amplitude, of course, you can see that you have a disappearance of these striations, okay? And on the right-hand side, it's the same type of observations, except that in that case, propagation is first in vacuum and then switch to air. You can see that in that case, you have no striations in vacuum and the formation of striations when the environment is switched to ambient air. So what is really remarkable in that case is that the presence of these striations can be considered as an evidence of some environmental assistance. On this slide, you have an illustration of possible interactions between environmental effects and some loading history effects, which are more representative of the actual loading that can be seen during service. So in that case, it's in the case of a low alloy high strength steels used in some helicopter rotors components. So on the left-hand side, we compare the fatigue crack-off rates obtained in air and in vacuum. And you can see that, especially at low delta K value in the near threshold region, we have quite a large fatigue crack-off rate enhancement with about 30 factor on the crack-off rates. And this fatigue crack-off enhancement tends to reduce when the delta K value is increased. When now looking at the fatigue crack-off rates obtained on the same steel with the same environmental conditions, but by considering this type of loading patterns, which is constituted of a baseline loading with a load ratio of 0.7, and every 10,000 cycles of this baseline loading, we introduce 100 cycles characterized by a higher mean stress or a higher load ratio, in that case 0.78. So the idea is to introduce some overload effects, which is supposed to induce a retardation in fatigue crack propagation. And indeed, when we compare, for instance, in air, the fatigue crack-off rates obtained with this type of loading compared with constant amplitude loading, the fatigue crack-off rates are delayed by this type of overload. However, when now we compare the fatigue crack-off rates obtained in air and in vacuum under this type of loading, we can see that we have almost no environmental effects in the low delta K region, and that environmental assistance only appears when we increase the delta K value. So that means that it seems that it is the opposite from what is observed under constant amplitude loading, where the maximum enhancement is observed in the low delta K region and tends to disappear at high delta K value. But actually, the analysis of these data demonstrated that, in fact, there is no real interaction between loading history effects or retardation effects and environmental defects. What is observed here is just a direct consequence of these differences observed under constant amplitude loading. Another example of possible interactions is the effect of the load ratio, especially near threshold. So here, in the case of a structural steel, on the left-hand side, we compare fatigue crack-off rates obtained in vacuum, in air, just like in the previous example, but also in an atmosphere constituted of nitrogen with some traces of moisture, namely 150 ppm of moisture. And what is surprising in that case is that it seems that the threshold value is higher in air or comparable to vacuum, and the lowest threshold value is obtained in this intermediate atmosphere containing only traces of water vapor. So this can look contradicting with the fact that we assume that water vapor is responsible for the highest fatigue crack-off rates in most environments. But actually, this results for more complex interactions between the fatigue crack-off process and environmental effects, especially, as we will see, due to the formation of oxide layer on the crack flanks that will promote crack closure effects. And indeed, as soon as we are able to measure and take into account the crack closure effects by estimating the delta Kf value, you can see that we have something which is, again, consistent with the prevailing role of water vapor, since the lowest fatigue crack-off rates are obtained in vacuum. Here we have an intermediate behavior represented by this mixture of nitrogen and traces of water vapor, and the highest crack-off rates obtained in air. However, we can notice that for this atmosphere with only traces of water vapor, we have a threshold value which is comparable to the one observed in air. And this was also studied, for instance, by Soresh and Ritchie in the United States. These are very famous results. This type of observation is similar to the one that I have shown before. Here in helium, you have some traces of water vapor. So that means that for a high load ratio, you have a comparable near threshold behavior. But at low R ratio, where crack closure effects are prevailing, you will obtain a higher threshold in air than in helium containing traces of water vapor. And on this graph, you have some measurements of the oxide thickness on the fracture surfaces in air or in, again, hydrogen containing traces of water vapor. And what you can see is that in ambient air near threshold, here you have an oxide thickness, which is much more important than in other environments, or even in ambient air when considering a higher value of the load ratio. So that means that near threshold, at low R ratio, you have a kind of wedge effect induced by this thick oxide layer, which will in turn induce a shielding of the crack tip and reduce the effective value of the stress intensity factor range at the crack tip. And as a consequence, in most cases, the threshold in air will be higher than the threshold measured in inert or environments with only very small traces of water vapor. But what is important to note is that this is beneficial from the point of view of the global fatigue crack-off rate resistance. fatigue crack growth resistance. However, at high low ratios, the shielding induced by closure will be extremely limited. And in addition to that, as you can see here, this is partly due to the fact that the oxide layer will be much lower in that case. So you will have a combination of a limited shielding by crack closure, but still the presence of the fatigue crack growth enhancement by water vapor. And as a consequence, the threshold in air will be lower than the threshold in inert environments. So from all these examples, we can deduce some methodological aspects. So our objective in the following will be to try to identify the specific environmental effect on the crack tip damage and not on the overall fatigue crack growth resistance, in particular by taking into account the shielding induced by crack closure effects. And for that, we will proceed along two main steps. First, we will have to determine the intrinsic fatigue crack growth resistance. That means in an inert environment and after crack closure corrections. And then by comparing the fatigue crack growth rates obtained in an active environment such as ambient air and in an inert environments, but also by comparing the fracture surfaces, we will get insights into the mechanisms operating at the crack tip. So let me say a few words about what I mean by intrinsic fatigue crack growth resistance. So this intrinsic fatigue crack growth resistance has to be determined in an perfectly inert environment. So you have to limit as far as possible the presence of water vapor. And also, as I explained before, by taking into account the crack closure effect that can reduce the effective stress intensity factor range at the crack tip. So when doing that, you can observe different types of crack propagation mode. So the most classical, which is observed here in the case of a single crystal of aluminum zinc magnesium alloy, oriented for easy gliding, but with two different heat treatments, one overage, one underage. So in the case of the overage alloy, here you have the notch, the crack emanating from the notch. This is the loading direction, the crack growth directions. You can see that we have a crack path, which is quite straight and perpendicular to the loading axis. So this is what we will call the intrinsic stage 2 propagation, while here in the case of the underage alloy, you can see that again, here you have the notch, and you can see that you have an extremely straight crack path with a crack propagating within the slip system, which is activated during the cyclic loading. And so this will represent what we will call the intrinsic stage 1 propagation. So the stage 1 is a crystallographic cracking mode or slip band cracking mode. And the stage 2 is characterized by propagation, which is macroscopically perpendicular to the mode 1 loading axis. But in these alloys, especially, in some cases, you can also observe a propagation mode, which is somehow a mixture of these elementary propagation mode. That means that from a macroscopic point of view, the crack path is perpendicular to the loading axis. But if you look at the microscale or at the scale of the grain, you can see that within a given grain, the crack propagation takes place along a single slip system, and you have to initiate another slip system in the adjacent grain in order to resume the propagation. And at the end, you have this type of zigzag crack path or rooftop crack path. And when you look at the fracture surfaces, you have the presence of these crystallographic facets, which are also indicative of this crystallographic propagation at the scale of the grain. And this is what we will call the stage 1-like propagation, which is similar to the stage 2 at the macro scale and to stage 1 at the micro scale. When now we compare the intrinsic stage 2 fatigue crack propagation data obtained here in different grades of steels, you can see that we have almost a single relationship as soon as crack closure effects are taken into account. And this can be depicted by a fourth power law. And this is the same here when you compare different type of alloys. You have the crack-off rates expressed as the parameter delta Kf divided by the Young's modulus that you can assume to be the strain intensity factor instead of stress intensity factor. And again, you can see that we have almost a unique relationship for these different type of materials, steels, titanium alloys, aluminum alloys. And so we propose to describe this intrinsic relationship by this equation, accounting for the fourth power law dependence with respect to this parameter. And it is noteworthy that this fourth power law dependency can be predicted by different theoretical models that you can find in literature. So now that we have characterized the intrinsic fatigue crack growth behavior, let me move to the analysis of ambient air. So in literature, this has been addressed, for instance, by Bobway and co-workers, and has been described in the form of a sequential process taking place at the crack tip. So first, you have the transport, consisting in the axis of the active species towards the crack tip. Then you will have the physical adsorption of these molecules, for instance, water vapor molecules, on fresh surfaces formed at the crack tip, and then a chemisorption process leading to the dissociation of the water vapor molecules, and in particular with the formation of hydrogen atoms. And some of these atoms can then ingress into the material and can diffuse within the cyclically deformed region at the crack tip, where the ambleting reaction takes place. But what is important to note is that in this analysis, although we have a sequential process, and Bobway identified two rate controlling limiting cases, but even if we have this sequential process, there is only one embrittling mechanism, which is supposed to be a hydrogen embrittlement mechanism. So on this slide, I've listed some of the hydrogen embrittlement mechanisms. So my purpose here is not to discuss these mechanisms, and I guess that during the course of the day, you will have more explanation about this. My message here will be just to say that any of these mechanisms can take place at the crack tip. But if we come back to the influence of water vapor, here are some results from literature by Bradshaw, Wheeler, or Pao and Vey, for instance. What you can see is that indeed, when you compare the fatigue crack growth rates obtained in air and then increase the water vapor pressure, you have a slight increase in the fatigue crack growth rates, which at high water vapor pressures are comparable to the one obtained in ambient air. Again, confirming the prevailing role of water vapor even in ambient air. On this slide, you have the same type of results here in the case of a high-strength low-alloy steel, but here the water vapor pressure is fixed to a very low value, 10 to the minus 3 pascals. And here we have some data obtained at different frequencies for fixed values of the delta key parameter. And you can see that for any delta key value, you have the same type of behavior with a high fatigue crack growth rate at low frequencies, then a transient regime, and the plateau here corresponding with higher frequencies. And this type of behavior was interpreted as follows. At high frequency, it is assumed that due to the low water vapor pressure, the intrinsic crack growth rate is too high to form an adsorbed monolayer of water vapor molecules at the crack tip. As the frequency is progressively reduced, more and more water vapor molecules are adsorbed at the crack tip, and this enhances the crack growth rates. And finally, on this plateau, we assume that we have the formation of a uniform adsorbed monolayer at the crack tip. And the lines, continuous lines on this graph, are the results of an equation that has been established to account for the adsorption kinetics. And this is described here. So the basic equation is the one that I presented before, where we introduced this critical displacement parameter d star, and we assume that this critical displacement is affected by the coverage rate theta, according to this equation. So the coverage rate theta has a value comprised between 0 and 1. 0 means there is no adsorbed molecules at the crack tip. And in that case, the value of d star will be the one determined in our inert environment. And theta equal to 1 means that we have a saturating adsorption process. And in that case, d star value will be equal to d star 1. And the question is then to determine the variation in this theta value as a function of time for different loading conditions. And for that, we have to write the equation for the axis of active species at the crack tip, for the adsorption kinetics, and also take into account the crack growth rates that will in particular control the surface that needs to be covered by adsorbed molecules at the crack tip. And finally, we obtain this equation, and by solving this equation, we have the variation of theta as a function of time that we can then introduce to predict the value of d star and to predict the fatigue crack growth rates, as I mentioned before. What is important to note here is that in these equations, especially for the axis of active species, we take into account the crack impedance effect, which is due to the fact that here the crack will behave as a narrow channel connecting a control volume at the crack tip and the external environment. And due to the very low partial pressure, in that case, the pressure in the control volume can be less than the water vapor pressure prevailing in the environment. And this in particular explain the transition here as the delta key value is increased. And we also collected different data on different alloys for different environmental conditions, generally low water vapor pressure conditions. And again, we observed that we have quite a unique relationship, which is characterized by the same fatigue crack growth rate enhancement factor, but again, with the same fourth power law dependency, which is the reason why in the basic fatigue crack growth equation, we did not change the exponent and only the coefficient. So I think I'm running out of time, so maybe I do not have time to detail this. Just to mention that in some cases, here in the case of iron aluminides, in some cases you can have a competitive adsorption between water vapor and oxygen, as described by these equations. And the point is that in that case, in an oxygen atmosphere containing some traces of water vapor, this competitive adsorption process lead to the fact that the fatigue crack-off rates obtained in this oxygen atmosphere is similar to the one obtained in vacuum, while, for instance, in argon, with the same water vapor content, in a low delta K region, we have almost the same fatigue crack-off rates than in air. So again, here we have a beneficial effect of this competitive oxygen absorption process. Finally, at the end, we analyzed the near threshold fatigue crack-off rate enhancement of steels or aluminum alloys or titanium alloys along the superposition of two mechanisms, namely the water vapor adsorption process, which will enhance the intrinsic stage 2 propagation, but it can be also stage 1-like propagation that will rapidly switch to stage 2 propagation. So water vapor adsorption will enhance the stage 2 propagation, but again, we're still the fourth parallel dependence. And when some critical conditions are satisfied in terms of water vapor partial pressure, or due to the fact that the cyclic deformation will be constrained in a very small microstructural unit, typically within a grain, you will have the triggering of the hydrogen-assisted regime that will induce much higher fatigue crack-off rates. And again, here I do not discuss the precise nature of this hydrogen-assisted regime. And just to finish, in order to describe the sequential effect of water vapor adsorption and then hydrogen assistance, we introduced this equation relating the fatigue crack-off rate to the effective delta K value with this superposition of the fourth parallel equation describing the adsorption, as I explained before, and here an empirical, I would say, equation taking into account the hydrogen effect. And by using this equation, we are able to nicely depict the near threshold behavior here in the case of a high-strength low-alloy steel. So just to finish, and I will skip the section on high pressure of hydrogen unless you really want to see it. My message will be first to emphasize on the fact that the fatigue data established in air, generally for model identification or for design curves, integrate sometimes some complex couplings with environmental effects. And my suggestion would be that it would be better to base this type of analysis on intrinsic data, as I showed during my talk. And the second point is that I hope that I've convinced you that the action of ambient air in the near threshold region is due to the combination of two distinct sequential mechanisms, namely water vapor adsorption and then hydrogen-related mechanisms. But the point is that today we have still numerous logs associated to the limited information of the local crack tip response to the presence of this moisture or dissolved hydrogen in order to have a complete description of the process at the crack tip.